Hello everyone. Thank you for joining this talk today. This talk is about stochastic model for time varying millimeter wave beam gains with user orientation changes. With ever increasing need for higher data rates and to accommodate large number of mobile devices, 5G cellular communication technology has moved towards millimeter wave bands. These bands range from 30 gigahertz to 300 gigahertz with large bandwidths available for wireless communication. While these bands can accommodate large bandwidths, they have few propagation issues like excessive path loss, attenuation due to atmospheric gases and precipitation, blockage, and scattering. To mitigate these issues, beamforming is used. Beamforming at millimeter wave helps in focusing transmitted signal in specific direction and also the reception in specific direction. With beamforming, we have new challenges. With narrow beams at the transmitter and the receiver, we have very large number of beams to look out for best beam to transmit from and receive from. Number of beam pairs to sound can be in the order of 100 beams or even more. User movement and user orientation changes necessitate frequent beam reselection. User orientation can change by 100 to 200 degrees per second for typical user movements. Here we show a toy example for sounding with 4 transmit beams and 4 receive beams. The base station transmits the pilots from each of its beams in a sequential order and in a burst. And these bursts are periodic. At the user, it measures all the BS transmit beams from one of its receive beams in one pilot burst. Receive beam 1 is measured here, say beam 2, 3, and so on. Further, because of the large number of beams that are sounded, the measurements are partially outdated and by different extents at the time of beam selection. If we select the beam with largest measured beam gain, as is conventionally done, we can experience severe degradation in performance. This motivates us to predict the beam gains given the beam gain measurements that are partially outdated and by different extents. In this paper, for 3GPP SCM, we propose a modified bivariate Nakagami-m model to accurately model the joint statistics of beam gains at any 2 time instants. This applies to both positive and negative power correlation cases. And it models user orientation changes and non-stationarity of the channel. And we further show an application with a novel beam sounding and selection approach that accounts for the partially outdated beam gain measurements given user orientation changes. Let us first look at 3GPP spatial channel model. It is a stochasto-geometric model. It models multiple antennas at the transmitter and at the receiver. This MIMO channel is given by the expression here. It has 2 components. One corresponds to line of sight and other non-line of sight. Non-line of sight component involves multiple clusters and each cluster made up of multiple rays. It models angle of arrival and angle of departure distributions that are critical in MIMO channels. This model matches well with various channel measurement campaigns. It is for this reason this is adapted in 3GPP. However, SEM does not provide a statistical model for the gain of a beam pair at one or more time instants. To handle this drawback, we propose a modified bivariate Nakagami-m model. And this characterizes in an analytically tractable manner the joint statistics of the beam gains at the times of measurement and data transmission. Here we define bivariate Nakagami-m for positive power correlation case. Here m is Nakagami-m parameter. Omega represents mean power at a given time t, and rho represents the beam power correlation at time t and t plus tau. This is a known bivariate PDF. However, its applicability to SEM is not discussed and verified in the literature for millimeter wave channels. So in the spatial channel model, negative power correlation is possible. Here we show the power correlation coefficient as a function of lag tau for the given set of parameters. We observe that the power correlation can be either positive or negative. Intuitively, a negative correlation occurs when the beam goes out of alignment. Now, bivariate Nakagami-m is not even defined for the negative power correlation case. To further understand the PDF, we show that level set contours of a bivariate PDF for positive and negative correlation cases with the same magnitude of correlation. These PDF and level set contours are generated from 100,000 traces of 300 millisecond long each. Here, x-axis and y-axis represent the beam gain normalized by the square root of mean power omega at that time. Here we observe that for positive power correlation case, the level set contours have 45-degree line as a major axis and 135-degree line as a minor axis for this contour. Similarly, for the negatively power correlated case, for this case, the level set contours have 135 degrees line as a major axis and 45-degree line as a minor axis. Further, we observe that both these PDFs have a common peak location. Here we have two new results. One, we provide an approximation for peak location of bivariate Nakagami-m. The two, bivariate PDF for negative power correlation case. In this slide, we show the result for peak location of bivariate Nakagami-m based on our result. We plot the normalized peak location coordinate m1 as a function of power correlation coefficient rho for the given set of parameters. We have shown the value measured from the empirical bivariate PDF and compared it with the proposed numerical solution. It matches within 1%. The other coordinate m2 behaves similar to m1. So on this slide, we give the steps to obtain bivariate PDF for negative power correlation. We first normalize the random variables with the square root of mean power such that both random variables are unit power. Then rotate the random variable vector by 90 degrees in the counterclockwise direction around the center. Then scale back up, where we remove the normalization with respect to beam power gain. With these transformations, we obtain a new PDF as shown below. We now have a different scale factor to make it a valid PDF. In this slide, we verify the proposed model by plotting the conditional cumulative distribution function. We plot the conditional CDF of beam gain at time t plus tau, given the beam gain at time t for multiple values of beam gain. It is accurate up to 2 orders of magnitude for both positive and negative power correlation cases. For the positive correlation case, conditioned on the increasing value of beam gain, the CDF of the channel gain at time t plus tau shifts to the right, while for the negative power correlation case, it shifts in the opposite direction, that is to the left, as expected. Having come up with accurate probabilistic model, we here show an application of MBN for beam selection problem. A quick overview of the setup here. As we saw earlier, BS transmits pilots from all of its transmit beams in a burst. And such bursts are repeated periodically. User measures with one of its receive beams on each of the pilot bursts. We measure S receive beams in one beam selection cycle from here to here. The last R pilot bursts, highlighted in blue here, measure top R shortlisted receive beams. Okay. The top R beams are those beams which have higher chances to be the best beam. Okay. In the setup, we use the time varying spatial channel model between transmitter and receiver. We model a time varying user orientation that is known to the user. Here we present beam sounding and selection rule. based on predicted SNR. We compute predicted beam power using the MBM, which is the mean beam power conditioned on the past beam measurement. Beam selection rule is to choose the beam with the largest predicted rate in n data slots. The top R beams are shortlisted for measurement based on the top R largest predicted rates. We obtain predicted power for both positive and negative correlation cases, as shown here. The predicted power is a function of correlation coefficient, mean beam power, and beam measurement. We provide average rate results for benchmarking here in this slide. We plot average rate as a function of peak SNR for the proposed method PBR and two other methods. One being conventional rule, where the best beam is selected based on the power measurement only. Second being non-causal Gini method, in which Gini already knows the best beam for future. Here we observe that the proposed rule achieves higher average rate compared to than the conventional rule, and the gap between the two increases as SNR increases. The PBR is close to Gini, showing that the proposed method is near optimum. On this slide, we show the top R probability, which is the probability that the best beam is in R shortlisted beams as a function of user orientation change rate. The higher this probability, the better is the ability of the beam selection rule to shortlist the receive beams that are likely to be selected and measure their beam gains. This probability is always 100% for the Gini aided rule. For R is equal to 3, as the user orientation change rate increases, the top R probability markedly decreases for the conventional rule, while that of the PBR remains above 98%. The behavior of the fall in the top R probability is same for R is equal to 1 as well. Now we shall conclude. In this paper, we proposed a novel and tractable modified bivariate Nakagami-m model for the bivariate PDF that characterizes the time-varying PDF evolution of non-stationary beam gains. This accurately captured the effects of user orientation changes. Further, it led to a new beam sounding and selection rule. For more details, please refer to our transaction paper shown here. Thank you for listening in.